Welcome. In this video I'm going to be telling you about the rational root theorem. But first I should probably remind you about a rational number. So I'm just reminding you that a rational number is the type of number that you might think of as a fraction. It's really something that could be expressed as a fraction. So something that is a rational number would be obviously a half. But obviously, whole numbers, integers are rational as well because you can think of them as divided by 1, so it's negative 12. But even something like 4.5, that's something that is going to be a rational number because I could write that as 9 divided by 2. And irrational numbers, I think probably up to this point, the one that you'd be most familiar with would be pi, right? In geometry class. Ratio of diameter to circumference, or whatever it is. And that one they've discovered over time is an irrational number. Okay, another one that's irrational that we've seen in this class is the square root of 2. Okay, and it turns out the square root of any number that's not a perfect square is going to be irrational, but that's beyond the scope of what we're talking about here. Another irrational number that we're going to run into later in this course, I'm just going to throw out there, is called e. And you may have heard of it, you may not have. Either way, in this class, e is just going to be some number that happens to be between 2 and 3 that math people happen to be interested in and that we'll learn more about in later courses. And that's just reminding you about what a rational number is. Alright, so here it is, the rational root theorem. Basically, what it's saying is that any possible rational root of a polynomial with integer coefficients can be expressed as the ratio of two numbers that are each kind of like factors of numbers we're seeing in the polynomial. And I think it would make the most sense for me to actually just start with the example. So list all the possible rational roots of the polynomial x to the 3 minus 8x to the 2 plus 11x plus 20. Okay, the big thing is identifying the constant term and the leading coefficient. So I'm gonna be real explicit about that. Okay, so I'm gonna highlight the constant term a0. Okay. And that's the number that doesn't have an x attached to it. Okay, so in our case, that's going to be 20 on the example. The leading coefficient, we have a little bit more experience identifying that. We've been talking about that quite a bit in this unit, and I think the last, maybe just this one. With the leading coefficient, we mean the number that's attached to the highest power of x. So in this case, we're looking over here, we're not really seeing anything. We know that that's 1. So they're saying that our possible x values are of the form p divided by q, okay, where p is a factor of the constant term. So up here, we have to think about factors of 20. And by factors, I mean numbers that if I divide 20 by them, I will have an integer, okay? So obviously there's 20 and 1. So I'm going to say 20. We'll come back to 1, try to, go in order from greatest to least. Okay, 10 times 2, 5 times 4, and obviously 4 times 5. So we need 2 and 1. Okay. But for our purposes here with the rational roots, we need to also consider the negatives, right? Because if we divide 20 by a negative 5, we're still going to get an integer. We're going to get negative 4. Okay, so we need to think about plus or minus all of these numbers. And then the denominator will be q, which will be some factor of the leading coefficient. Now, in this particular case, with this polynomial we're looking at, the leading coefficient is 1. So really our only options are plus or minus 1, which isn't going to really change anything. So I would say these are my possible rational roots. Okay, so plus or minus 20 over 1, plus or minus 10 over 1, plus or minus 5 over 1, plus or minus 2 over 1, or plus or minus 1 over 1. Had there been another factor, had it been, say 2x cubed, we would have needed to consider what would have happened had we done 20, 10, 5, 4, 2, and 1, all divided by 2. But we'll see plenty of examples like that. So let's think about this in general. Okay, how I'm going to set it up in general is I'm going to kind of always say p divided by q, and I'm going to go up here and I'm going to list the factors of p. Pardon me, not factors of p, factors of the constant term. So in this case, factors of a0, and down here we're talking about factors of a n. And then we're going to just combine them, in as many ways as necessary. And sometimes we'll see there's a little bit of overlap and it's not as many possibilities as we would think. All right, and then another example would be like a multiple choice question, like which of these is not a possible rational root of the polynomial. And so I think this concept lends itself really well to multiple choice. And just throw that out there. Okay, so, but this one, I'm going to kind of run through it as if I was solving it for real, and and then eliminate based on that. But I think if you already were comfortable with this, there's probably a faster way to determine this. Okay, so I'm going to say that any of the factors of this, or pardon me, the roots of this polynomial are going to have the form p over q. And to use the same color scheme I was using before, it's going to be p is going to be a factor of the constant term, which is -8. And q is going to be a factor of the leading coefficient, which is 5. Okay, so this will be good because this has a mix. Okay, p could be plus or minus 8, obviously. Okay, and then the factors of 8 would be like 4 and 2. And there's not really anything else we're going to be able to have plus or minus 1, though. And then q, it's going to be a factor of 5. So 5 and 1. There's nothing else that divides 5. Okay, so we're looking at our options, and our options for denominators are 5 and 1. So we're not going to be able to eliminate anything based on that, because A has a kind of implied denominator of 1, and B and C and D all have denominator 5. So we're going to be having to look at the numerator. And I'm noticing D here, 3/5 is not going to be a possible root of the polynomial because 3 is not in my list up here. Okay, so that's going to be how we would work a problem like that. Another way we can use the rational root theorem is to help us maybe factor a polynomial that otherwise we wouldn't be able to factor. If you look at this is a third degree polynomial, and we would be able to factor it if it had the parallelism we needed to do group and factor, but I'm just not seeing it. It's not going to happen. So one thing that we could do is we could just try rational roots and hope that something would work. And then, if we got lucky, then we could divide that out and see what we had left. And in this case, since we've got a cubic polynomial at degree 3, if we were able to divide out one of the factors, we'd be left with a quadratic, which we know we can always either factor or solve using the quadratic formula. So we've got a good chance of solving this one. So we're going to start with the possible rational roots. So we know it's going to be of the form p over q, where p is a factor of -6, so 6, 3, 2, or 1. And q is going to be a factor of the leading coefficient, which is 1 because I'm seeing 1x to the 3. Right, so my options are 6, -6, 3, -3, 2, -2, and 1, and -1, which is honestly a lot of options. And so I kind of need you to think critically about, is he really going to make me try 8 numbers? And I'm not. So I would recommend always starting with 1. Yeah, that's just my personal recommendation for my class, is always start with 1, maybe -1, and pretty much if one of those isn't a root of the polynomial, I'll probably bump up the degree and give you one of them, or give you a picture of the graph or something. But I just need you to, as a student, think critically about, what kind of trying and failing is going to be realistic in this class. I don't need you to run a bunch of factors through synthetic division and fail a bunch of times. Okay, so let me show you what we're going to do. So we're going to start off with just an educated guess of x equals 1. All right, we're going to start basic. And we're going to check to see if it's a root of the polynomial by seeing if, when I plug it in, I get 0. And one way that we've learned how to evaluate a polynomial is with synthetic substitution. So 1x to the 3, -7x to the 2, positive 12x, and -6. I set that up. I'm going to run 1 through there. I run through the algorithm like we have previously in this class. Okay, sure enough, I get 0. Okay, that's a good sign. And now I think, okay, well, this is showing me what I have left. Okay, and I think now it would probably be good for me to kind of write out what I'm working with here. Because when I did synthetic substitution, I really also did synthetic division. So if I divided the original polynomial by x minus 1, I would get x squared minus 6x plus 6. Okay, which kind of makes the equation in black down there true. And then kind of the next thing I think to myself is, okay, can I factor the quadratic that's in parentheses? I'm trying to think of two numbers that multiply to positive 6 while adding to negative 6, and it's just not working for me. So when I'm trying to factor and it's not happening, I revert to the quadratic formula. Okay, so if I'm trying to solve this equation where this equals 0, which is what we're doing, we're finding the roots of a polynomial. Okay, I've got it factored, so either x minus 1 is equal to 0, and that's when x equals 1, or x squared minus 6x plus 6 is equal to 0, and that happens when x is equal to 6 plus or minus the square root of b squared is going to be 36 minus 4 times a times c is 24, so 36 minus 24 is 12, all over 2a. Right, so these are my roots, right? So I could maybe put them off to the side. I could say x equals 1, x equals 6 plus the square root of 12 divided by 2. You could simplify that if you needed to, or 6 minus the square root of 12 divided by 2. Okay. Those would be my roots. Alright, now that's pretty much all of the problem types I'm going to give you about the rational root theorem, but I figured since I had you here and I told you a theorem about rational roots, I might as well also tell you a theorem about irrational roots of polynomials. So if x equals a plus the square root of b is a root of a polynomial with rational coefficients, then x equals a minus the square root of b is also a root. And we just saw that happen when we applied the quadratic formula. So, I mean, I wouldn't say that this is totally surprising. The fact that it's true for any polynomial with rational coefficients is, decently surprising. Unfortunately, I'm not going to be able to prove that for you in this video. We're just going to work with the theorem a little bit. Okay, the only thing I'll throw out before we do is that a plus the square root of b and a minus the square root of b are what you might hear called radical conjugates in this course or maybe in a later course. So I just wanted to heard that before. All right. So we're going to write a standard form polynomial of minimal degree that has zeros at x equals negative 7 and x equals square root of 5. Okay. So I'm going to start, and I'm going to write you a standard form polynomial, and by that we mean it's like not factored. We've actually multiplied it out. Okay, that has zeros at x equals negative 7. Okay, so y is going to be equal to some number, some leading coefficient, times x minus negative 7. Multiplied by x minus the square root of 5. Okay, and I know I just said that if x equals a plus the square root of b is a root of a polynomial with rational coefficients, then x equals a minus square root of b is also a root. But I just kind of wanted to point something out. Since I forgot to type in, write a standard form polynomial of minimal degree with rational coefficients that has zeros here and there, that I can write a standard form polynomial of minimal degree that has these two zeros and doesn't have that other zero. A times, all right, I'd end up doing some FOIL, and I think without any loss of generality here, I'm going to assume a is 1, and it's not going to change my point. Okay, so I'm going to just assume a is 1 and distribute this, do a little bit of FOIL. X times x is x squared. On the outside, I have minus square root of 5x. On the inside, I have plus 7x. And the last would be minus 7 square root of 5. I guess we just had to write it in officially approved standard form. I might call that 7 minus the square root of 5x minus 7 times the square root of 5. But that's a standard form polynomial of minimal degree. Okay, so if we need rational coefficients, that means, we don't want this square root of 5 nonsense floating around. We need to have x minus, or pardon me, not x minus. If we have positive square root of 5, that's 0 plus square root of 5. We need to also have 0 minus square root of 5. So let me clear this all out. So, and if we add rational coefficients, then we're going to have x equals -7, x equals square root of 5, which, as I said just a second ago, we might think of as 0 plus the square root of 5. Okay. We'll also need x equals the negative square root of 5, right, which we could think of as 0 minus the square root of 5. Okay. And if we have these zeros, then we'll have a polynomial with rational coefficients. So I've got some number, which I'm just going to keep assuming it's 1 if it doesn't tell me to make the leading coefficient any different, which we will work problems where it does, but just maybe not quite yet. So x minus -7. Then over here I'm going to do x minus the square root of 5, and then on the other one I'm going to do x minus the negative square root of 5. Okay. Right. I mean, you can multiply these in whatever order you want, but I think it would be wise to multiply the minus square root of 5 and plus square root of 5 one first, just because these kind of look like a difference of two squares, right? And it's going to work out that way. Okay, so when I multiply x minus the square root of 5 times x plus the square root of 5, I'll get x squared minus the square root of 5 times x plus the square root of 5 times x, and then minus square root of 5 times square root of 5. Okay, but the square root of 5 times the square root of 5, I mean, you could think of it as, okay, well, that's exactly what 5 is, or you could say that that's the square root of 25, which is going to be 5. Either way, this is going to be x squared minus 5. And then we've got some number, which I'm just going to assume is 1 starting now, times x plus 7 times that. Okay, and now I'm going to do just a little bit more distribution. X times x squared, that's going to be x to the 3. Okay, to put standard form, maybe I'll do them in descending power order. That'd be 7x squared, negative 5x. And 7 times negative 5 would be negative 35. Okay, so that would be a minimal degree standard form polynomial with rational coefficients that has zeros at x equals -7 and x equals square root of 5. Just in order to make that happen, we also need to have 0 at x equals the negative square root of 5. The last problem I think I'm going to be working on video for you here is kind of the same concept, but one where we actually have a number plus the square root of another number. Okay, so write a standard form polynomial of minimal degree that has rational coefficients. I'm going to need to add that. Rational coefficients and a double root at x equals 0 and a single root at x equals 2 plus the square root of 3. All right, so I'm just going to copy that in. Alright, so we're just going to kind of set up our factors like we've done before. So it says a standard form polynomial of minimal degree. It doesn't say anything about the leading coefficient, so I'm going to assume the leading coefficient's 1. So I'm going to start off with y equals 1 times x minus 0. Now since this is a double root, I'm going to need to throw an exponent of 2 on there. And the next one, this is just where you need to be a little careful, is x minus, and then we're going to, in parentheses, put 2 plus the square root of 3. And after that, we'll have x minus, and then in parentheses, 2 minus the square root of 3. So now we're going to need to do a bit of cleaning up on this. So x minus 0, we're just going to call that x, right? We don't have to carry that x minus 0 around. So we've got x squared. And then if I distribute the negative on this one and on this one, we'll have x minus 2 minus the square root of 3 multiplied by x minus 2 plus the square root of 3 when I subtract that negative square root of 3 on the far right. Okay, so I've got my factors, and I just need to multiply this all out, and I should get myself a standard form polynomial of minimal degree that has rational coefficients. Okay, so I'm going to go over here to the side and actually do that multiplication here. Okay. So I've got x minus 2 minus the square root of 3. And maybe doing this multiplication hopefully will help you see why if a plus the square root, like if you do this, that you're going to get rid of all of your square roots, which is all the stuff that can make your root irrational. Okay, so x minus 2 plus the square root of 3 was the second one. All right, so we're just going to multiply this out. I probably should have paused for this, but it's going to be all right. Okay, now positive square root of 3 times the negative square root of 3, that's going to be negative 3. All right, now I'm going to combine all these terms together. And, notice how the negative root 3x and the positive root 3x canceled, and the positive 2 square root of 3 and the negative 2 square root of 3 canceled. You'll see that happen every time if you work enough of these problems. You'll recognize that pattern. That's really the mechanism that's working here, that's serving to ensure that we've got rational coefficients to our polynomial. All right, so over here, the last step is just going to be distribute that x squared, so it's going to be x to the 4 minus 4x to the 3 plus an x squared. Okay, so that'll be our standard form polynomial, minimal degree, double rooted x equals 0, rational coefficients, and a single rooted x equals 2 plus the square root of 3. Also just happens to have a root at x equals 2 minus the square root of 3. All right, that's all for this video. Thanks for watching.